this is going to be our unit that covers all of the inductor, okay? So the inductor is a circuit component that relies heavily on the principles of magnetism and electromagnetic induction. So let's first of all consider the word induction. What does induction mean? Induction is the process by which a changing magnetic field produces an electric field. So that's why the word induced current is present here in our curriculum. An induced current is a current that is induced by a changing magnetic field. So when we say that we have an induced EMF, the equation is a bit more complex. The equation, our induced EMF, I'm going to call it E sub I, is the negative derivative of magnetic flux with respect to time, okay? So we can see that the relationship is not with respect to the field, but it's with respect to the flux. Okay, now let's do a gentle reminder of what magnetic flux is. Magnetic flux is going to be our integral of the magnetic field dotted with the area vector. Okay, so our magnetic field, the magnitude of our magnetic flux could change if our magnetic field changes, if our area changes, or if the angle between them changes. So understand that there are three contributions to the magnitude of the magnetic flux, okay? Now the equation you have on your reference table is this, that the EMF is equal to the path integral of the electric field with respect to the length differential, dotted with the length differential, which is equal to the negative derivative of magnetic flux with respect to time, okay? So what does this part of our equation mean? Well, this part of our equation for this particular unit is not important to us because this is a relationship that we discussed all the way back in, I can't remember if it was unit 1 or unit 2, that voltage or EMF is equal to the derivative of is equal to the integral of the electric field with respect to distance. Okay, so that was a concept we covered in the previous units, and I think the equation we had for that was that the electric field is the derivative of electric potential with respect to distance x. Okay, so this is a concept that was useful to understand in previous units, and I guess the relationship application in this unit is to say that the induced EMF by the change in magnetic flux induces an electric field throughout the wire. Okay, I have never seen this equation applied mathematically. I have only seen it present to say that, oh hey, just a little concept reminder, since we're inducing an EMF, that also means we're inducing an electric field. I've never seen anyone need to do calculations with that. Okay. Of course, if you find a problem or you need extra help with that part, just come to me, let me know. We've got a Discord server. Moving on from there, we are going to start discussing the concept of electromagnetic inductance in the inductor circuit component. And the inductor circuit component is very often or almost entirely a solenoid. Okay, I don't think you will see anything apart from a solenoid in your circuit analysis. So a reminder of what a solenoid is. Solenoid is a component that is a length of wire that is curled around itself and has many, many, many loops, okay, as such. Such that if I were to look through the solenoid from this end, I'd be able to see a perfect circle, which is the circle formed by the rings of wire as they orbit around the center, okay? So the induced EMF in a solenoid is equal to the number of turns in the solenoid, capital N, times the negative derivative of magnetic flux with respect to time. Now let's actually understand what this equation is telling us, okay? How do we interpret the negative derivative of magnetic flux with respect to time? So let me draw a diagram for you. Okay, let's say I have a single loop of wire, like this. Okay, and there's no current flowing through the loop of wire. It's just a loop of wire. Okay, and I have a magnetic field coming out of, going into the page. I think that's the symbol X, yes. Magnetic field going into the page through the circle formed by that loop of wire, okay? Which means I have a magnetic field and I have an area through which that magnetic field is passing. That is the area of my circle, okay? So, if I wanted to decrease the magnetic flux through my circle, I could constrict the circle. I could make the circle smaller. That would decrease magnetic flux. I could decrease the magnitude of the magnetic field, or I could rotate the loop of wire so that the angle theta is changing. In order to understand why a change in the magnetic flux induces an EMF is to understand the magnetic field, okay? A magnetic field has inertia. If you don't know what inertia means, it means that the magnetic field is something that likes to stay constant. The magnetic field really doesn't like to change, okay? And also what it means is if I try to change the magnetic field will work against me. The magnetic field will try to undo any change that is done unto it, okay? So let's understand what that would mean, okay? If I decrease the magnitude of the B field, if I decrease the magnitude of the magnetic field, that would be indicated by smaller x's, if you were wondering. If I decrease the magnitude of the magnetic field, then the portion of this loop of wire is going to say, hey, wait a minute. The magnetic field's changing. I don't like that. I really don't like the fact that the magnetic field's changing. Let me try and counteract it, okay? How can a loop of wire counteract this change? By adding its own magnetic field, okay? So if the magnetic field decreases, the wire will induce a magnetic field to increase it again. It'll work against the change, okay? So if the magnetic field was originally coming out of the page like this, and now the magnetic field's smaller, the induced magnetic field from the wire needs to be pointing out of the page again to add to the now decreased magnetic field, okay? So if the wire needs to create a magnetic field pointing this way, we're going to use the right-hand rule, wrap our hand around the wire, and discover that the induced EMF is going to induce a current flowing this way through the wire. Okay? Such that the difference between the initial and the final EMF momentarily will be accounted for by the increased EMF provided through this current, okay? Such that if we consider only this section, only the flux, the magnetic flux through this loop of wire, the magnetic flux hasn't changed, okay? Because whatever was lost due to the external B field was gained back when the wire counteracted the change, okay? And the same concept can be viewed if I try and increase the magnetic field. If I were to create a magnetic field that goes further out of the page, much further out of the page, like this, then the wire was like, no, man. I need to pull you back in, I need to keep you and put you back where you were. So the wire is going to induce a magnetic field going this way to counteract the change in the magnetic field, the magnetic flux. So I do this, I do right-hand rule, and I discover that now current is going to be flowing this way. So that is why there is a negative symbol here. The induced EMF will work to counteract the change in magnetic flux with respect to time. And in the event that you're dealing with a solenoid, this induced EMF is done for each and every loop in the solenoid. That's why you have a multiplicative relationship when you're dealing with a solenoid. That's why the number of loops present is a factor in our equation, okay? Now let's consider the electronic component that is the inductor. So an inductor has an inductance. and the inductance is represented by the letter L, okay? Inductance of a component is the degree to which the component does not want to have a change in current, okay? If it has a high inductance, the component really doesn't want to have a changing current flowing through it, okay? If it has little or no inductance, the component has no problem with changing currents flowing through it, okay? The reason for that being is because the magnetic field doesn't like to change, okay? If passing current through a component is going to create a magnetic field where there originally was none, then that magnetic field has inertia. The magnetic field wants to stay zero, okay? So passing current through a component that will create a magnetic field is going to cause that component to oppose the current that you are trying to apply to it, okay? So maybe it might be useful for me to draw this for you in a circuit diagram, okay? If I have a battery here, I hope we remember our circuit diagrams when we covered them, and the symbol for an inductor is the curly loop of wire, as demonstrated as such, okay? Be careful to draw your curly loop of wire as if it were curly, because if you draw your curly loop of wire with straight lines like this, that's not an inductor anymore, that's a resistor, okay? So be careful to take care of the curliness of your lines. Anyway, we know current is going to be flowing this way through our circuit, and so the current is going to come to this component, an inductor. Okay, if the current flows through this inductor, this is going to create a magnetic field. And the magnetic field doesn't want to change. The magnetic field wants to stay zero, okay? So what's it going to do? The inductor is going to create an EMF that is exactly equivalent to the EMF of the battery, such that no current is going to flow through the circuit and no magnetic field ends up being created. Now, it's important to recognize that this only happens on a very small time scale, okay? Eventually, after some time has passed, the EMF from the battery will overcome the inductance of the inductor, current will begin to flow through the inductor, and a magnetic field will begin to be created. So since virtually every inductor in every circuit is a type of solenoid, it would be useful to have an equation to determine the inductance L of a solenoid. So that is given to you on your reference table, that the inductance of the solenoid is equal to the permittivity of the core, which we will discuss in just a moment, multiplied by the number of turns in the solenoid squared, multiplied by the cross-sectional area of the turns, divided by the length of the solenoid, okay? Now, important in this analysis, the length of the solenoid does not refer to this length, does not refer to the length between point A and point B. It refers to the length of wire used in the making of the solenoid, okay? So this might be one-dimensional length of 2 centimeters, but maybe 10 centimeters of wire was used. You would use the 10 centimeters of wire in this calculation. We know number of turns, that's pretty self-explanatory. Area, if you look at the solenoid from one end, you would see just a circle. Calculate the area of the circle, the area of the loop of wire. The permittivity of the core, okay. So when you create a bunch of loops around here, those loops are formed around a core, okay? In this particular example, there is no core. So what do I do here? Well, it would be the permittivity of nothing, the permittivity of free space. The permittivity of free space is mu naught, which is a constant you have on the front page of your reference table, okay? So if you have no core, your mu is mu naught. Oftentimes, to increase the inductance of a solenoid, there is an iron or a different type of metal core inserted through the loops like this, okay? And that increases the inductance. And you would either be given it or you would be given the inductance and you need to calculate it, okay? The next equation you have on your reference table is an equation for the potential energy stored in an inductor, which is equal to 1/2 times the inductance times the current flowing through the inductor squared, which means an inductor can store potential energy just like a capacitor can. Okay? I'm foreshadowing something. We'll come back to that. Anyway, so the reason for that being is because if, in the capacitor example, if I were to take away the battery from a capacitor, then the capacitor would remain charged. The capacitor would continue storing charge and electrical energy. If I were to remove the battery from an inductor, then since the inductor does not want the current flowing through it to change, then the current flowing through it won't change. And current will continue to flow through the inductor, and it will continue to flow through the open circuit because the inductor wants to keep current constant. So that will result to a massive buildup of charge on each end of the open circuit, okay? And that only lasts for maybe a few microseconds. But the point is that current continues to flow, and an inductor stores potential energy in the form of current. So that brings us to our next equation on our reference table, that the electromotive force induced by an inductor is equal to the negative inductance times the derivative of current with respect to time. Okay? Now this equation is applied in two senses. First of all, if I were to pass a magnetic field through this inductor, that magnetic field, or rather changing magnetic field, would induce an EMF, okay? That EMF I then set equal to this EMF, and I get that the derivative of magnetic flux with respect to time is equal to inductance times the derivative of current with respect to time. And this derived equation from the combination of these two then tells me the relationship between the change in magnetic flux through the inductor and the current induced through the circuit. Okay? Let me close this off so it's more easy for us to understand. Now, the other sense of the equation is if I were to connect this back up to a battery again, and I had a switch in the circuit, then first off, when the switch is open, there would be zero current flowing through the circuit. Okay, so the initial current would be zero. The second that I close the switch, then the battery will begin to force current through the circuit. Therefore, the derivative of current with respect to time started at zero, and now we got a high current. The derivative of current with respect to time is very high. Okay? So since the derivative of current with respect to time is very high, the negative direction of current is the direction in which the EMF will be induced, okay? Like I told you before, if we connect a battery, in the very short time after we connect the battery, the inductor will create an EMF that is equal in magnitude and opposite in direction to the EMF of the battery. Okay, so if the battery starts to send current this way, the inductor will create its own EMF that will try and send current this way, opposing the flow of current, and at the initial instant, zero current will flow because the EMF supplied by the battery is equal to the EMF of the inductor. And since electric charge always flows from high potential to low potential, there is no way for charge to flow. So you keep hearing me reference the fact that initially the current flowing through the inductor is zero, and after some time, current begins to flow, okay? Since the current flowing through the inductor is non-constant, we have a new derivation very similar to the derivation for the capacitor equation that we need to perform for the inductor. Okay, so I want to find the current flowing through the inductor as a function of time. Again, we're going to do our setup. We're going to set up using Kirchhoff's loop rule. Okay, so we say that the total EMF is equal to the EMF supplied by the battery, which is equal to the EMF dissipated by the rest of the circuit. Now this equation is useful in determining the current flowing through an inductor inside a circuit that is comprised of both an inductor and some resistance. Okay? Now, this equation works if you have an inductor without any resistors. It's useful to derive the equation with some resistance in the circuit, because if you derive the equation with resistance, you can just plug in 0 for all the resistance terms and simplify your equation if and when you do not need resistance terms. Anyway, if we do our setup with Kirchhoff's loop rule, we know that the total EMF in the circuit is going to be the EMF supplied by the battery, which is going to be equal to the EMF dissipated through the circuit, which is equal to the voltage drop across the resistor, IR, which is equal to the voltage drop across the inductor, L di dt. Okay, so now here I have a differential equation. I have current flowing through the circuit, I, and I have a derivative of current with respect to time. Let's isolate my derivative right here. So to do that, we're going to get epsilon minus IR over L equals di by dt. And if I want to do my separation of variables, I'm going to get 1 over L dt is going to equal 1 over epsilon minus IR di. Okay, that's my separation of variables. Now I need to integrate both sides. Okay, what's important to know is that we are going to be doing definite integrals here. We are integrating the left side from some initial time 0 to some final time t. We're going to integrate the right side from some initial current 0 to some final current I that we're going to evaluate at. Okay? First off, the evaluation of the left side of our integral is very easy. It's just going to be t over L evaluated 0 to t, which simplifies to just t over L, equals the integral from 0 to I of our antiderivative here. Okay? So first thing I'm going to do is I'm going to do a u substitution. I'm going to set u equal to epsilon minus IR. So my du by di is going to equal negative r. Because if I differentiate this with respect to I, derivative of constant 0, derivative of negative IR is negative r. Okay? So from there, I'm going to want to get di by itself. So du over negative r equals di. So if I rewrite this, this is going to become 1 over u epsilon minus IR, which represents epsilon minus IR, times di, which we now know is du over negative r. So the resistance of our circuit is going to be a constant, so I'm going to pull that out, negative 1 over r. Okay, and since it's a constant I pulled out of my integral, I might as well bring it to the other side. Multiply both sides by negative 1. Multiply both sides by r. Negative tr over L equals the integral from 0 to I of 1 over u du, which is therefore going to equal the natural log of u evaluated 0 to I, which equals the natural log of epsilon minus IR evaluated 0 to I. So let's not forget about this side of the equation right here as we do our evaluation. So that's going to be the natural log of epsilon minus IR minus the natural log of, if I plug in 0, I'm just going to get the natural log of epsilon, which if we do our log rules is going to equal the natural log of epsilon minus IR. I can't write today. That's the wrong side of my eraser, but anyway, natural log of epsilon minus IR divided by epsilon, again, because subtraction can be converted to division in natural logarithms. And now we have finished our evaluations, okay? Now that I'm here, I'm going to step back and say, wait a minute, I wanted current as a function of time, so I need to isolate I. So first things first, I need to raise e to both sides. E to the negative tr over L is going to equal epsilon minus IR over epsilon. I'm going to multiply both sides by epsilon right here. I'm going to subtract epsilon from both sides. Epsilon e to the negative tr over L equals, I'm sorry, not equals, minus epsilon equals negative IR. Multiply both sides by negative 1. Epsilon minus epsilon e to the negative tr over L equals IR. Factor out epsilon. Epsilon times 1 minus e to the negative tr over L equals IR. Epsilon over r times 1 minus e to the negative tr over L equals I as a function of time. And that is our derivation. Complete. One thing to note, just like in the capacitor derivation, we have a time constant, the Greek t. On your reference table, you will notice that the time constant is equal to the inductance of your circuit divided by the resistance of your circuit. Therefore, our current as a function of time can be rewritten as the EMF supplied by the battery divided by the resistance of the circuit multiplied by 1 minus e to the negative t divided by the time constant. If we do that substitution, and that equals our current through the inductor as a function of time. Again, I see this derivation pop up a lot on FRQs, so it would be very useful for you to know how to do this derivation. Very long, I know. So before we move on to the next part, I want to reiterate a concept of the inductor just for it to stick into your mind. Okay? At time equals 0, once the switch is initially closed, the EMF induced by the inductor opposes EMF by the battery, therefore 0 current flows through the circuit. Therefore the current behaves as if it were open circuit at time equals 0. Then, after a long time has passed, once the current flowing through the inductor has reached its maximum, it has stabilized, then the inductor behaves like closed circuit, behaves like a normal wire. The current flows through it as if it had 0 resistance. Okay? The final topic in all of E&M is, it's a doozy, pal. This is like Joker smiling at Batman. You got no idea what I got in store for you today. Okay, the final topic is the LC circuit. The circuit that comprises of a capacitor and an inductor. Okay, so what does this behave like? So first of all, we're going to start by saying that the capacitor is charged at time equals 0. Okay, so if it's charged at time equals 0, then it's going to function like a battery. It's going to induce an EMF throughout the circuit. Okay, so initially there will be an induced EMF. The inductor will work to oppose that EMF, and after some time, current from the capacitor will begin to flow through the circuit, and the inductor will behave like a closed circuit, just a wire. So current will begin flowing through regularly. Then, after some time, the capacitor will become discharged and will no longer be able to supply an EMF. However, current flowing through the inductor does not want to stop flowing because the magnetic field has inertia. Okay? So, the current flowing through the inductor will begin to charge the capacitor in the opposite polarity that it was initially charged before. So if it was originally plus minus, then as the inductor begins charging the capacitor, it will become minus plus. Okay, so let's conceptualize what's going on here. The capacitor forces current through the circuit. Current starts flowing like this. Okay, so that current is current supplied by the capacitor, and the capacitor starts discharging. Once the capacitor is discharged, current will continue to flow through the inductor, and therefore the inductor will begin to discharge into the capacitor. So this is a conservation of energy. You have electric potential energy initially stored in the capacitor. Capacitor discharges, it transfers that energy to potential energy stored in the inductor. We go from electrical energy stored as charge to electrical energy stored as current. Okay, so the description of this behavior can be modeled with a conservation of energy equation. The potential energy stored in our capacitor is equal to, if we consult our reference table, where is it? 1/2 Q delta V, which equals the potential energy at the maximum stored in our inductor, which equals 1/2 Li squared. Now, since potential energy is determined by electric potential V, we can set the electric potential from the capacitor equal to the electric potential from the inductor. Electric potential from a capacitor can be determined from our capacitor equation, which equals Q over the capacitance of the capacitor. And the electric potential supplied by our inductor is going to be the negative of the inductance times the derivative of current with respect to time. Okay? Now, you guys may not see it yet, but we're about to introduce a very, very cool topic. Okay? I apologize if you guys hear fireworks in the background. I'm recording this near July 4th. Anyway, so what is current? We remember that current is the derivative of charge with respect to time. Therefore, the derivative of current with respect to time is equal to the second derivative of charge with respect to time. Okay, so I'm going to rewrite this equation over here and say that Q equals negative LC. I just took my C, moved it to the other side, times the second derivative of charge with respect to time. Now, some people may not see it yet, so I'm going to help them out. Okay? I'm going to move my LC back to the other side, and I'm going to say d squared Q over dt squared equals 1 over negative LC Q. Let's use the same Q's. Okay? Now, here's what I'm going to do. I'm going to change my variables around a bit. Okay, I'm not going to change the equation at all, I'm just going to change the letters. Let's say instead of Q, I use the letter X. And let's say that 1 over negative LC, the inductance and the capacitance of our circuit are going to remain constant, so this is just going to be some constant. Let's call it negative K. So I get d squared X dt squared equals kx. You guys seeing what I'm seeing? I'm seeing the differential equation that describes simple harmonic motion with a spring. Therefore, what we have here, current being discharged through the capacitor and then being recharged into the capacitor. Capacitor discharging through the inductor and then the inductor recharging to the capacitor. It's woom, 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 woom. It's oscillatory motion. You guys are going to hate me so much. This is such a hard thing. Oh boy. We're dealing with oscillations in a circuit. Current is oscillating back and forth periodically. Okay? So, let's return to what I have here before. The second order differential equation that describes the LC circuit. So we are also given on our equation sheet that omega, the angular velocity of an LC circuit, is equal to 1 over rad LC. Okay, I'm not going to derive that for you because it's on your reference table. Why would you need me to? Okay? Since we have the angular velocity of our LC circuit, we can then scroll on our reference table down to the mechanics equations and find the equations that govern oscillatory motion. Equations like, why can't I find it? It's here somewhere. Come on, work with me here. Here it is. X equals x max times the cosine of omega t plus phi. Or charge on the capacitor equals the max charge on the capacitor times the cosine of omega t plus phi. And you'll notice here that since cosine oscillates between 1 and -1, the charge on our capacitor will oscillate between plus minus and minus plus. Okay, so the electric potential on our induced by the capacitor is going to oscillate from positive and negative values. So given this equation, charge on the capacitor divided by the capacitance of the capacitor equals the potential difference across the capacitor as a function of time. And if we wanted to find the current flowing through the circuit as a function of time, we would just take the derivative of charge as a function of time, right? So I of t equals the derivative of q of t. Okay. So, from here, I wanted to leave you with one advice for the E&M exam, or the Physics C both exams, for that matter. This topic right here, the analysis of LC circuits with oscillatory motion and differential equations and all this, this is a very high-level advanced topic in the course, okay? I have never seen this tested on an AP exam, not in multiple choice, not in FRQs. If you're in a pinch, if you're cramming, and you want to know what you should skip, skip this, okay? Don't practice this. But of course, if you want to get a 5, and if you want to get a perfect score, of course practice this. My point being that in the Physics C course, it's a very difficult course. It's a very high level, very advanced course. Therefore, there is significant curving of grades, okay? So you have the ability to maybe learn and master and memorize 85, 90% of the course and do away with 10 or 15% if you really, really don't like 10 or 15%. My tip to you guys. Thanks for watching. Enjoy life.